Great. So hi everybody. Just a little bit of background. So my name is Collin Foster. I'm a graduate student working with Dr. Panerai at UIUC, and I have had absolutely nothing to do with the development of PuMA, but I'm very happy to have just been asked to give a brief little overview on X-ray micro CT. The hardware that's involved, and just the type of data that we're working with and that will typically be flowing through the PuMA pipeline. So just as a brief introduction, so this is just an overview of micro CT that I think is approachable for all levels of experience. But so X-ray micro CT or X-ray microcomputed tomography enables non-destructive evaluation of the inner surface topology of a material. And so this allows us to do things like track deep and close porosity, complex part geometry, and subtle to dramatic changes pre and post an experiment. And so this is kind of just a classic canonical video that I'm sure a lot of us have already seen, but it is of an astronaut being scanned at the advanced light source. And so just kind of an overview of the process that kind of goes on with taking a CT image. So let's say that we wanted to study the actual parachute cord on the Orion mission. So we would just cut off a small sample of that and put it in our little test holder there. We would put it in box 3, which is the micro CT device shown here to just be a lab-based system. It will sit between our source and detector, which is shown on the left and the right respectively. The result of the micro CT will be a series of 2D radiographs, which will be stacked on top of one another to actually form our 3D image of this microstructure. And just before getting into some more of the details, I just wanted to touch on the history, just because it's kind of interesting. So it was actually discovered by Wilhelm Roentgen, and it was actually achieved the first Nobel Prize in physics. So he essentially discovered it on accident, performing experiments on a Crookes tube. But I just thought it was kind of interesting now that it's become such an integral part of medical imaging as well as the research that we do. And I also just thought it was kind of funny that one of the very first experiments that he did, deemed it was safe enough. He actually did a CT scan on his wife's hand, where we can see the multiple phases of kind of the soft tissue. We can actually see the hard tissue of her bone, and of course, her wedding ring, which I hope stayed on after performing experiments on it. After that, so just to kind of go into more of where the computed tomography part of that comes in. So during the 1970s, as computers were becoming more and more advanced, so it was actually begun to be a solution for medical diagnosis. And that's because of permitted, safe, convenient, non-invasive locating of cell mutations, bone irregularities, and high-density ailments such as tumors, let's say. And so just the mathematical algorithms integrated just made MCT way more effective, much quicker, and shown here is kind of a before and after actually integrating mathematical transforms such as a Fourier-based algorithm. Okay, and so now talking into how we use micro CT in some of the work that we do. So an X-ray, it's as a photon emitted from a source. The material that it passes through, it's going to absorb or attenuate the beam as it passes through the matter, and then it's finally detected by the detector as radiographs. The sample is rotated 180 or 360 degrees to collect several hundred or even thousands of radiographs in total. Measurements or the variation in photons can be collected through a 2D or just a line detector or through a 3D array, which is how we do our 3D tomography. And most of all, what we use it for primarily is to visualize the relative density through intensity measurements. And shown here is just kind of the workflow through, of course, our meteor crashes down to Earth. We take a small piece of that. And it's an excellent example of a multi-phase material with multiple material densities in the form of various density grains. And then we use our software such as Dragonfly to actually visualize our multi-phase material. Okay, and then just to talk briefly about a bit of the hardware that actually goes through taking a lab-based micro CT scan. Like I had said before, we have our X-ray source that actually produces our X-rays over on the left-hand side. We have our sample, which sits in the middle and it rotates 360 degrees. And then finally on the right-hand side, we have our detector, which is equipped with normally a CCD or a CMOS sensor. And then not to dive too deep into it, but it's important to mention, the detectors themselves, they use the photoelectric effect of a semiconductor to actually convert those incident photons that have been attenuated by the matter into electrical charges through a series of photodiodes. The scintillator is actually the first thing that the X-ray radiation hits, and it actually converts that it converts that radiation to visible light. And so this is all just to say that, the detector actually plays a really important part in actually determining the voxel size. And so oftentimes there's a compromise between field of view and voxel size that you want to actually achieve with your scan. And so as is kind of intuitive that if you want a larger field of view, there's often going to be a compromise in voxel size, which is just your relative resolution. And depending on the scale that you're trying to image, that's a very important parameter that is decided by the researcher. Okay, and then back over on the left-hand side, we have our source. And so one of the more important aspects that we can actually control with our source is the current and the exposure time, which actually comprises X-ray intensity, also known as grays, which are just X-rays per unit area. And so essentially, the higher the intensity or the higher the current and exposure time, the higher number of incident photons that are actually passing through our sample. This has the benefit of, if you have a higher intensity, typically you can help reduce that kind of salt and pepper noise that can be apparent with some micro CT scans, as shown on the image on the right-hand side. And then of course we have voltage or energy, depending on the type of system that you're using. So voltage, kind of the thought behind it is that if you have a material with a higher Z or atomic number, a higher voltage is required to actually penetrate that material. But there can be issues with your scan if your voltage is too high, such that the material is unable to attenuate any of that high voltage X-ray photons that are passing through it. And so in order to achieve sufficient contrast, you might have to spend some time actually tuning that voltage or that energy. And so just to touch on another way of acquiring data outside of the lab setting is that many people in our field, they use synchrotron micro MCT for a way of actually acquiring their data. And so synchrotrons provide a unique capability in that they actually solve a lot of the issues that come with a lab-based system. So one of the primary issues with a lab-based system is that they are prone to beam hardening, which is essentially just changes in X-ray photon energy as it actually passes through your sample. Typically, synchrotrons are better equipped with more complicated detector systems that are able to achieve higher resolution, as well as they're more apt equipped for reconstruction, which can actually make that process from data acquisition to a usable TIFF stack or image stack much faster. And most of all, you have a very, very high flux of energy coming off of those beam lines that you can actually use to penetrate through experimental devices and actually perform in situ testing. And so what I mean by that is that you can have your sample, let's say it is in some sort of rig that is performing a tensile load on it. Those X-rays are actually able to penetrate that load cell, be able to attenuate through your sample, and you can actually see, depending on your temporal resolution, the material and how it actually responds to that tensile loading. And so, like I said, this is an excellent application for actually doing micromechanical response testing, thermal cycling, even up to 1800 C, your choice of chemically reactive environment, whether it's going to be reactive, inert, or just in vacuum. And then, of course, what's super interesting is when you're able to combine all of these for a dynamic process. And so another, on that same note of in situ micro CT, I just think a really interesting development that has come recently outside of the national lab facilities is the ability of gantry-based in situ micro CT. And so this is being developed by a team over in Belgium, where they have, instead of the sample actually rotating 360 degrees, they have their source and their detector that actually rotates around their sample. So that enables you to put your in situ testing rig on the platform without any worrying about wire twisting or anything like that. And shown here on the left-hand side, an example of a compression test on an aluminum foam. And then this video that's hopefully is playing for everybody on the right-hand side is the collapse of a beer head that looks like somebody, probably the worst pour you've ever seen in your life. But pretty interesting stuff in terms of the developments for in situ micro CT. Let's see. And then just to talk, more so about some of the applications for in situ micro CT. This can be used with some of these sophisticated deep learning softwares to actually track relevant regions of interest. For example, so this is some work done by some of our colleagues over at CU Boulder, but this is just a tensile test on a unidirectional CMC, and they actually used micro CT to actually track micro cracks through their sample. And then over on the right-hand side, synchrotron radiation was utilized to take a really high fidelity scan and also incorporate tiling such that a larger sample could be produced as it underwent just a stepwise loading. And then of course you have your high temperature applications. So shown here is over at the Swiss light source. It is just an example of real fiber forms, which Joseph was showing earlier, as it actually underwent an oxidation experiment. And so that video might be a little glitchy for everybody, but in essence, that sample is rotating very fast. The acquisition system is fantastic over at the Swiss light source. So that enabled them to actually capture in time the oxidation of those carbon fibers. And so, what is really the point of all this? And really it's to inform multi-physics simulations at the end of the day. As Joseph had, explained in more detail a little bit earlier, of course, we start with our CT scan. Here is just shown just a single ply silica carbide composite. And then moving over to the right, we have our real geometry, that can be informed or used to inform an analytical geometry generated in such softwares such as TextGen, which Federico will talk in more detail about how PuMA actually uses that. And then, of course, you have your surface and your volumetric meshing using, the software of your choice. And then, of course, we have, what we're interested in is those effective property simulations. So in all, thanks for listening to my little spiel about micro CT, but it's a super valuable tool for ex situ and in situ testing, of course. Scanner improvements have led to really high fidelity accessible data at even a university level facility. And as we'll talk about, and this is really where software such as Dragonfly have really come in great these last couple of years, is that the ability to digest and discriminate, those terabytes of data is enormously important. And I'm sure it will be a growing area of research to come. So yeah, that is it for me.